You know, when it comes to chemistry, speed is often everything. But what actually controls how fast a reaction goes? Is it really as simple as just, dumping in more ingredients? Well, that's the big question we're going to dive into today with chemical kinetics, which is really just the science of how fast things happen and, more importantly, why.
I mean, it seems like a pretty simple idea, right? You double an ingredient, the reaction should just go twice as fast. It makes total sense on the surface. But, and this is a big but in chemistry, your gut feeling isn't always the whole story. You actually need a rule book because, as you're about to see, the real answer, well, it's not always so straightforward.
Okay, so where do we find this rule book? It all starts with what's called the reaction rate rule. Think of this as the fundamental blueprint for a reaction. It's what tells us exactly how the amount of stuff we put in, the concentration, is tied to how fast that reaction will go.
And here it is. This is the rate law, and honestly, it's the key to this whole thing. It looks a little mathy, but it's simple. It just says the rate is equal to some constant K. Think of it as a special number for this specific reaction, multiplied by the concentrations of our reactants, which we're calling A and B. Now here's the secret sauce, the part that's kind of invisible but super important. Each of those concentrations, A and B, is technically raised to a power. We call that its order. In this example, the order is just 1 for both, so we don't write it. But trust me, that little detail is going to become a huge deal in a bit.
All right, so now that we've got our rule book, the rate law, we can finally go back and tackle that original question. Let's put this thing to the test. We'll apply it to a real problem and see what shakes out. So here's the exact setup. We're given this rate law. Rate equals K times square brackets A times square brackets B. Simple enough. The challenge is this. What happens to the reaction speed if we double the amount of reactant B, but, and this is key, we keep the concentration of A exactly the same? We're only changing one thing. Okay, no guesswork allowed here. This is all about pure, simple logic. Let's walk through the equation step by step and see how this one little change totally reveals the answer. So, to really see what's happening, we need to set up a classic before and after comparison. On the left, you've got our starting point. Let's call it rate 1. The concentration of B is just, well, B. But on the right, that's our after scenario, rate 2. See how we've plugged in our new condition? The concentration of B is now 2B. Just by looking at these two equations side by side, we can figure out exactly what that change did. Okay, let's walk through the logic here. Step 1, we start with our new equation for rate 2, which is K times A times 2B. Now here comes the key move, step 2. Because this is all just multiplication, a little bit of simple algebra lets us pull that number 2 right out to the front. And look what that leaves behind. That bit in the parentheses, Ka, Kb, what is that? That's our original equation for rate 1. So for step 4, we just substitute rate 1 back in, and boom, we get our final relationship, rate 2 equals 2 times rate 1. So we followed the steps. We did the logic. What's the final answer? What actually happens to the rate? The math has spoken. And there you have it. It's 2x. The new reaction rate is literally twice the original speed. So it turns out our first guess was right. For this particular rate law, doubling the ingredient actually did double the speed. It's a perfect 1-to-1 relationship. But wait, the answer being 2x isn't actually the most important part of this. The real takeaway is the process we just used, because it shows us something much, much bigger. This isn't just about solving one little problem. It's about understanding a fundamental concept that lets chemists predict, and more importantly, control the speed of pretty much any reaction. So let's put all the pieces together. Remember that invisible exponent I talked about at the beginning? Well, it has a name. It's called the reaction order. And this is the whole shebang right here. Because our reactant B had an order of 1, we call it a first-order reactant. And what that means is that its effect on the rate is perfectly proportional. You double the concentration, you double the rate. You triple it, you triple the rate. See? The reaction order is basically the secret code that tells you exactly how changing the concentration will affect the speed. So, when you boil it all down, it really comes to this. If you can understand the order of a reaction, you have the key to controlling its speed. And that right there is the difference between just randomly mixing chemicals together and the precise, powerful science of chemical engineering. Okay, so we've totally cracked the case for a first-order reaction. But what if the rulebook was different? What if the rate law was rate equals K times A times B times squared? Now, B is a second-order reactant. What do you think would happen if you doubled the concentration of B then? You'd use the exact same logic we just did, but I bet the answer would surprise you. Something to think about. Thanks for tuning in.